Hey folks, Phil Zito here, and in today's episode, we are going to be talking about pressure control. So we're going to go over to the whiteboard, we're going to talk through some basic concepts around pressure control, and we are going to discuss kind of stack effect, pressure, wind, building pressure set points, static pressure in air handling units, etc. So we're going to learn all about pressure today. I do want to remind you that today and tomorrow are the last days of our tax day sale where you can get 20% off the cost of courses. So if you're at all interested in doing our training courses, make sure you take advantage of that. Okay, so far in this HVAC series, we've talked about space control, we've talked about air handling units, we've talked about psychrometrics, and now we're going to talk about pressurization. So if you think of a building, right? We draw out a building here. There's a lot of pressures being applied to a building. So just outside in the earth, as you walk around, you have atmospheric pressure. Now, obviously, as you go higher up, the air becomes less dense, you have less pressure. As you go closer to sea level, you have more pressure. Obviously, you go underwater, you have water pressure, right? So when we are in a building, there is actual pressure against the building. Now, depending on the density of the air, we may have to do different things with our building from a pressurization perspective. But what is pressure? Well, air has mass, all right? And I constantly hammer this in our control sequence fundamentals course, that air has mass. And it's really important we understand that because often we think of water having mass, we think of steam having mass, but we don't think of air. Air has a lesser mass, obviously, than water and steam, but it does have mass. So because of that, as we distribute air, which air is our primary mechanism for heating and cooling our spaces, as we distribute air throughout the building, we are moving a mass around, okay? And that mass exerts pressure. It exerts forces. And those forces are known as pressure. I see a pop-up. I just want to make sure real quick. Give me 1 second. Yeah. Okay. Are we live? Yes, we are. We're good. Okay. And my chat's coming through. Cool. Awesome. All right. Yes. So just wanted to make sure that there wasn't a volume issue. I was having an issue with a mic earlier today, and it was just being goofy, and I wanted to make sure that we weren't experiencing that. So if you guys can say that you hear me in chat, I'm just going to continue along unless I hear someone say that they don't, or see someone say that they don't hear me. I can kind of see it out of the corner of my eye. So as I was saying, with airflow and pressurization, right? So we've got a unit, let's say a VAV box, right? Inside a space. And we've got a air handler on the roof of the building. And that air handler is supplying air into the VAV, and then we maybe have exhaust. And I want to make sure that we understand there is exhaust and then there's relief, right? So exhaust is taking bad stuff out of the space. Relief is relieving pressure. So it's important that we understand those differences because when we are using 100% outdoor air units, we are typically using exhaust fans, right? We are exhausting that air out of the space because we're not recirculating it. When we're using relief fans, we're relieving excess pressure. And that becomes important when we positively pressurize our buildings. So we will switch, sometimes, we will switch between positive and negative building static pressure depending on the outside influences, whether we want air to come into the building or we want air to come out of the building. But our primary things that we're fighting against from a pressurization perspective, we're going to talk building pressure and then we're going to collapse into space pressure and then we're going to go into pressure control with a fan. So the primary thing we are fighting against from a pressurization perspective is going to be stack effect, right? So that's going to be the ambient pressure of air. That's going to be things like wind that is pushing against buildings because buildings are not perfectly sealed, right? Air can get in. That's called infiltration. And then if you overpressurize a building, air can actually get out. That's called exfiltration. Now, you've probably experienced high and low pressure buildings You've walked into a building and it's difficult to open the doors. It makes kind of a sucking sound. You can feel the air being sucked through the door. That is a negatively pressured building. So one of the quick ways to tell if you're in a space that is negatively pressured is to put a piece of paper against the door and see if that paper gets pulled through the crack or if it gets blown away. And that can give you an idea real quickly, it's not scientific, if you're in a positive or negatively pressurized space. So that being said, in a building, what we do to pressurize our buildings, right, is we either through a ducted relief / return or through a plenum relief / return, we will introduce air through the air handler into the building, either through VAVs or direct duct into the space, and then we will relieve the air out of the building. Now, we will use a relief fan or an exhaust fan, as some people call it. I really like to delineate between the two because I used to do a lot of healthcare work, and it was really important you didn't call the exhaust fans relief fans and you didn't call the relief fans exhaust, because if you're exhausting like a COVID patient room or someone who has SARS or something like that, those are going to typically be 8 to 12 feet up. You're going to see the tall exhaust stacks and you don't want to breathe that air, versus general relief air is not such a big deal if you're exposed to that. So that's why I keep hammering that difference. But the air is exhausted out, right? So we have air supplied in and we have air that is exhausted out. Now, how do we control pressure? There's a variety of different ways we control pressure. We have what's called volumetric offset and matching. That is a flow-centric pressure strategy. And what we will do is we will measure the flow that is going in and the amount of flow that's coming out, and we will either match, and we will go and say, okay, we're going to match flow, and that should keep us at a kind of normal pressure, or we're going to do an offset, either a negative or a positive offset, depending on how we want to influence building pressure. Now, we can also do what is called fan tracking. And this is something that you'll see sometimes where you have a VSD and it's got a 60% signal on the supply, and then you do a 60% signal on the return / relief. And the theory is that the relief / return fan is smaller, and thus with fan curves, you are going to get a positive scenario because you're going to be relieving less volume than you're supplying. So that's kind of the scenario. I personally like volumetric offset as my preferred strategy. I like to do that. I feel it gives a better granular level of control. It is definitely difficult, or more difficult, to drive building pressure with a volumetric offset than it is to just drive straight to the set point or to just set and forget doing speed matching. That being said, so that's building static, right? And with building static, we're aiming for anywhere from like negative 0.1 to a positive, or negative 0.1 to a positive 0.01, if I could speak this morning. This is, and these are extremes, right? Anything in between this. And typically during summer, you'll flux more towards the positive, and during winter, you'll flux more towards the negative, because in the summer, especially in the south, you want to push that hot, humid air. And remember that what we learned in psychrometrics, you're starting to see how this all builds together. What we learned in the psychrometrics video is that warmer, humid air has more mass than colder, humid air or warm, dry air. And so if you're in a climate that has a lot of humidity, then you're going to have greater pressure against the building. So you're going to have a greater positive pressure in order to force that air out, to keep it from coming in. But if we blow this up, right, if we expand this and we start to look at pressure control within the spaces, typically you're not going to experience pressure control within the spaces. Typically, you're going to make a selection of saying, hey, we're either going to put our building pressure sensor at the door, at the entry to the building, and in which case we're going to have to do signal filtering. We're going to have to account for the fact that as that door opens and closes, we're going to see a lot of what's the word I'm looking for? It's not air. We're going to see a lot of noise in the signal. We're going to see it spike up and spike down artificially because of that door being there. So you can do that. Another scenario is to put building static in the plenum somewhere in the center of the building. So that's for internal building static measurement. For external building static measurement, typically we'll see like a pressure sensor here and a pressure sensor here, or we'll see a pressure sensor on the actual AHU. I personally like having it on the buildings, and I like to do an averaging effect. That way I account for the effect of wind on that pressure signal. So that's for the outside pressure and then inside pressure, because we need to know the two so that we can tell if we're positive or negative. Sometimes, obviously, you'll see the cheap man's way, which is to put one in the air handler and one outside the air handler. And so you have one like in the return duct of the air handler, you'll have your building pressure sensor, and then you'll have right on the outside of the air handler, you'll have the building's outside reference. So the outside reference and then the actual pressure sensor right there. Now, that being said, I don't suggest you do that, but some people will do that and you'll find it's an inaccurate way to measure pressure. All right, so now moving to space. In my experience, there's a very select amount of spaces that you actually need to measure pressure in. Usually that's in the healthcare, that's in the life sciences vertical markets, a vertical market being a type of market, a type of business, right? So healthcare is a vertical market. It's a type of businesses, right? Hospitals, outpatient, inpatient, etc. And then life sciences is things like agriculture, Monsanto, pharmacy, etc. Those are where you're typically going to have to use like TSI pressure monitors within the space and outside the space to detect if the space is positive or negative. And in that case, you'll typically be using like a Phoenix Venturi valve VAV system, something similar, and you'll be driving that using typically like volumetric matching or volumetric offset in order to drive pressure in the space. Most of the time, though, we're concerned with building static pressure, and we will drive either our relief fan to drive that building static pressure, right? We will control building static pressure off of a variable relief, or we will have a offset, or we will have that signal matching, or we'll just have a static setting on our exhaust that's been kind of designed by Test and Balance, that setting. That all being said, if we blow up the air handler, right? So I know there's not an air handler inside the building, but I don't feel like erasing. So we're bringing it inside the building for graphical purposes here. But so we got our coil, we've got our dampers, right? And we've got our fan. What we're going to do is we're going to drive discharge air pressure. We're typically going to drive that. As VAV boxes close and open, that sensor is going to be adjusted. It's going to be impacted, and then we're going to drive to like a 1-inch or 2-inch static pressure set point, somewhere between that for inches water column. Now, that all being said, you'll often hear we need to install the sensor on a 2/3 run. Well, I don't like that definition because you don't want to just go down the longest duct 2/3. You want to do a actual analysis of what is a great representation of the diversity of your terminal units. So if you have a mix of VAV boxes, some are reheat, some are series fan, some are cooling only, you want to get a good mix. You don't want to just sample the cooling only. Or you don't want to sample just the reheat, because the reheat, especially in the wintertime, will all be sitting there at reheat minimum. So let's say reheat minimum's 300 CFM, and all of the cooling boxes are, 1,000 CFM for cooling max. You want to account for that. And if you're only sampling cooling or only sampling reheat and you don't have a good mix, then you're going to have a lot of noise and you're going to have to use signal filtering on your pressure sensor. So you want to be aware of that. So a good mix is more important to me than a 2/3 duct run for my sensor. So from a pressurization perspective, just to recap, we have buildings. Our buildings are affected by ambient outside air, the humidity, the speed of the wind, all of that's pressing against the building, and that's allowing air to infiltrate or exfiltrate the building. So we will go and control pressure. We'll have very low pressure amounts for building static pressure, because remember what this means. Like, I want you to realize this. Think of a door, right? And think of the pounds per square inch, right? PSI, pounds per square inch. If we have a high amount of PSI pressing against that door, like if we did 1 as our building pressure, that would be insane. You would not be able to open the door because you would have this air just pushing across the square inches of this door. You would have you'd have thousands of pounds of pressure on the door, and you would not be able to open that. So we really need to be cognizant that our pressure set points for building static pressure are actually quite low. Now, when we get into the air handler, you can see up to 4 inches water column on a really high pressure air handler. So just be aware that while it is pretty low in the building, we can get potentially high on the air handler side. And then obviously when we get into the hydronic space, we're typically commonly sitting somewhere between 20 to 50 PSI on the hydronic side for water, right? All right, I'm going to move over to my computer, see if we have any questions. And then we do have a webinar today on building automation careers. So I do have to be off this at 11:35, 11:40. All right, one thing I do want to leave you all with once again is, as I've mentioned multiple times across our past episodes, is that we are rapidly approaching the last 2 days of our tax sales. So if you want to save 20% off of our courses, use the coupon code TAXDAY at courses.smartbuildingsacademy.com. Additionally, I did pull a really good resource for you all to use from Train. They've been a great customer of ours. And while we are not sponsored by anyone, I want to be crystal clear on that. SBA is not sponsored by anyone. We take no money from anyone for sponsoring or anything. I will share resources when I find them to be valuable. And the Train Engineering newsletter is an extremely valuable resource. I have shared it in chat. It goes pretty in depth, including equations for pressurization. If you're a geek like me, I encourage you to read and memorize that stuff. That's kind of how I got to where I'm at by doing that. So I encourage you to explore that. That being said, I'll hang around for a little bit here. I am going to go and post the link to the webinar for those of you who are feeling squirrely and want to show up at this webinar. There is still space, and so I will send you the link to that in the chat. You can feel free to show up to that webinar at noon today, and we'll be talking through how to get a job in building automation. So that being said, as always, hit the subscribe button, then hit the bell so that you get notified. 11 a.m. on Wednesdays. It's going to be 8 a.m. on Mondays until my son gets done with his soccer season, because I just can't make 8 p.m. work during soccer season. That being said, thanks so much for being here. I will hang around for just a little bit, see if you have any questions. I hope that cleared up a lot of misconceptions around pressure control, gave you some ideas, gave you some things to explore around pressure control. And thanks so much for being here. I'm going to take a sip of water. Alrighty. Give a minute or two to see any questions that could potentially filter in, and then I will call the live stream. By the way, I just installed a fan in here because it gets ridiculously hot. Can you all hear that? Because it sounds really loud to me. But I should have noise filtering set up so that you can't hear it. Hopefully. Let's see. Alrighty. Cool. Well, seeing no questions or comments, I encourage you all to comment after this video. Make sure you ask questions. I will answer them. I will come and check what you ask and answer it to the best of my ability. So I encourage you to definitely take advantage of that. Thanks a ton for being here. I will see you all on Monday. Okay, James says he's typing a question. Well then, that works out. So, while you do that, I am going to get the lighting set up in here. I thought I had it turned on. Our building pressure set points seem higher in summer, 0.07, and winter is 0.03. That is normal, yes, because you are going to have all that humidity and everything pressing against you, Bruce. And so you are going to want to have a higher pressure in the summer. And then winter obviously being lower because you're fighting against less dense air. Remember, as the air gets colder, it is less dense, so it has less mass. So that is perfectly normal. And then as I've mentioned, some of you may have heard this. I think I mentioned it in our live office hours in our courses. If you have a building with a lot of doors, I highly encourage you to invest in air curtains. That or using, not corridors, what's the word I'm looking for? Airlocks, basically. Obviously not like space station airlocks, but basically where you have a door and then you have a corridor and then you have another set of doors. That will really reduce air loss, and that will reduce infiltration and exfiltration of air. And if you mix that with kind of a carousel door, that will also go and further decrease the impact with the pressure loss and pressure gain. Have I seen a control system that tracks outdoor air relief and exhaust air to pressurize a building? Yes, I have. I've seen that primarily in a lot of these condo buildings where they have a combination of exhaust in the condo units. They'll have a common exhaust, and then they have relief for the corridors, for the common areas. So, right, you have the common area, and that's typically served by a makeup air unit that serves the common area as well as the elevator shafts. And then the individual spaces are fed by fan coil units that feed into a common exhaust. So you'll see that. As you mentioned, there is in the toilet areas, you have toilet exhaust that feeds into a common exhaust because you're not going to recirc that air. Now, typically when you're doing those kind of scenarios, the relief is variable and the exhaust is common. So you have a common exhaust for these spaces, and then you have a variable relief because you're pressurizing with a makeup air unit, especially with condo buildings, which I think we're going to see a lot more of. I think you're going to start to see commercial real estate converted to condos because they got to do something with these assets. But you're going to see a common corridor, and then you're going to see your elevator shafts. All of that's going to be fed by makeup air, and then you're going to have fan coils, as I mentioned, in the actual spaces themselves. Hope that helps, James. Good questions, though. Good stuff. Alrighty. Perfect. Well, that being said, I am going to call it. I'm going to get ready for our webinar that's coming up in just a little bit. Hopefully I'll see some of y'all there. Look forward to talking to you. Thanks a ton, and take care.